Okay, this problem is 1982 E3. It is from the packet of practice problems that I gave you before you left. I think it's a nice one because it's an old, early, fairly simple one that makes you think a lot. In fact, I think that for a lot of these problems, thinking is what you ought to do first before you do any looking at what the problem is asking for. So let's do that here. There's two main things here I think we should look at. One is how the inductor behaves over time, and the other is what the switch does to the circuit. So let's take a look at both. A good way to think about an inductor early on in a circuit is that the inductor completely opposes any initial current flow. In this case, there will be no current in the circuit initially because the inductor is going to oppose anything that happens initially. However, after a long period of time, if the switch were to be open, let's say, then R and R would just be in series with each other, and this would be a fairly simple kind of circuit after a long period of time. You could simply get the total current by dividing the EMF of the battery by 2R, because these two resistors are in series. On the other hand, if the switch is closed at time t equals 0, and you let this circuit run for a long time, then that means that this resistor is being shorted out always. So initially we'd get no current at time t equals 0, but after a long period of time, this thing would remain shorted out. This thing would be behaving like a wire because there's no longer a rapid change in current, and so it's not having any sort of back EMF induced in it, and so you would just have E over R as your current in the circuit. Similarly, if we were to open the switch after a long period of time, then you would have had a steady state current of E over R. Opening the switch and letting the circuit reach a new steady state would get you back again to E over 2R after opening the switch. Sure enough, the first question asks, what is the current after a long period of time with the switch closed? That's going to be the inductor being ignored, the resistor only here because the second resistor has been shorted out. And sure enough, again, after the switch has been opened with this steady state current flowing in it for a while, now you have this R being included in the circuit. So after a long period of time, the new equilibrium state, the new steady state, will again ignore the inductor but have two resistors. We're being told for this graph that we should treat t equals 0 as the instant the switch is opened. So having been this value for a long time, once the switch is opened, it will eventually reach this value. In the next part, we're being asked for a differential equation for this current as a function of time, basically the differential equation that eventually gives us this. Because we are in the regime where the switch has been opened, we have 1, 2, 3, 4 things to write into our differential equation. Fortunately, two of them are going to be exactly the same. This could be written in a different way, but once you've got it in terms of the given quantities, you can stop. And as far as I'm concerned, this is a differential equation. It's got the function I and its derivative di dt in it. So that's it. The last question asks us to write an equation for the current as a function of time. Now, given how vague the language is here, write equation, this is back in 1982 after all, I think that we could go about this in a couple of different ways. One of those ways is to solve this differential equation using the full machinery of differential equation problem solving that you learned in calculus. And the second way is to cheat, just to write down an exponential function because you know that's what it has to be, and then figure out what your initial parameters have to be in that exponential function. The first thing that's good to do once you're close to a solution is to look at the extreme values for time. Here, it makes most sense to think first about what happens as time gets very large, because this exponential decay, this whole term goes away. And we can see that, in fact, the current does equal E over 2R, which we knew it had to be from the graph and from part B. The second thing to look at is that at the initial time t equals 0, when the switch is first opened, we know that the current in this circuit is EMF divided by R, and so that tells us what the C1 value has to be. So there you have it, a pretty clean solution for a pretty nice problem. And we used the full machinery of calculus to get the answer and didn't have to do any guesswork. Pretty nice. Of course, if you're running low on time, or if you just don't feel like going through all this nastiness, you can kind of cheat by knowing that this solution has to take the form of an exponential. So there you go. You can cheat by doing three simple things. One is knowing that the time constant is L over R. So that quickly gives you the value for C in the argument of the exponential. The next thing is knowing what the current has to be after a long period of time. So that gives you your A value, since this second term goes away. The third thing is knowing that the initial current has to be E over R. So that gives you an E over 2R and a plus sign.